All right, so now we're ready to do the last part C. It says a model for the radius of the second circle is given by the function f from 0 to 6 seconds, where f of t is measured in centimeters and t is measured in seconds. The rate of change of the radius of the second circle is given by this. So rate of change of the radius. So I'm going to think about this as another dr dt. This is a rate function. Based on this model, by how many centimeters, okay, there's an amount, does the radius of the second circle increase from t equals 0 to t equals 3? So this basically means I need to calculate from 0 to 3 seconds what is the antiderivative of this rate function f prime of t dt, and that will give me the number of centimeters that it's increased by. Be very careful with your notation here. It's a pretty straightforward problem. If you went back to chapter 6 or looked at your practice final, things like that, from the end of semester 1, this would have been a really easy problem on the final. However, a lot of people got a little sloppy or lazy in their notation and didn't get full credit for not writing the definite integral correctly. So then when we think about that, now we need to take the antiderivative. We could write it again this way. Plug the quadratic in there. Never forgetting the dt here, right? If this represents areas of all the little rectangles, this is the height of every rectangle and the width. We cannot forget the dt. All right, so the antiderivative of t squared, we have t cubed over 3 using the power rule, minus 4t squared over 2, plus 4t, evaluated from 0 to 3 seconds. So again, don't draw the integral here along with this bar notation, meaning we've already taken the antiderivative. We got a point for each of these so far. Now we just need to plug in and find our answer. So here when we plug in a 3, 27 over 3, this will reduce. 3 squared is 9, 2 times 9, plus 4 times 3. I can already see here if I substitute a 0 into all three of these terms, it would also just give me a 0. 9 minus 18 plus 12 gives us 3 centimeters. The final answer gave us the last point. So this was a great review of chapter 6 that we studied in December together, definite integrals, and an application of if we're given a rate, how definite integrals, we use antiderivatives to get the amount value back. We did that also in chapter 7 and a little bit in chapter 8 in third quarter. Thanks, guys.